speak into your caller real quick?
Check, check.
Hi everyone, welcome to yet another graduate seminar. Today we have Cooper, our new PhD student here, and he's going to be talking about a novel improvement to a classical number theoretic inequality. Yep.
Yeah.
Take it away.
Howdy. So yeah, this is a problem I worked on, or I was first introduced to when I was an undergraduate by a professor I worked with, Krishna Alladi, and yeah, he kind of suggested the problem in a seminar that he was giving, noting that a prominent number theorist now, Sanarajan, who's at Stanford, improved the inequality that he did when he was 17. So he was like, maybe you can do something too. And I was like, probably not. But then, and I was kind of right. However, I did do something. So, and that's what I'll talk about today. So, I mean, there's many ways to motivate what the theorem is saying. But I think probably the best way to do it is to just start with talking about sets of divisors. So we should start with just like this simple fact that, I mean, you probably noticed from like elementary school, which is that if you have a natural number n, and you consider just the set of divisors of n, you could say that basically this set has median root n. So, is this not showing up too well?
It's okay, but
This is brand new. Let's see, is this any better? I think it really is. Oh, wow. Oh, they got some duds in the math department office. That sucks. Kobe! Oh! I can't lose now. All right. So, yeah. So basically, okay, what do I mean by this? So like some examples would be like, if you take 30 and you look at its divisors, you got 1 and 30, you got 2 and 15, 3 and 10, 5 and 6. Also, if this becomes illegible at any point, just let me know. The square root of 30 is like 5 something, right? Because square root of 25 is 5. And it's sandwiched in between 5 and 6. And that sort of splits the set in half. Now, if you have a square like 100, obviously the square is, or the root is directly in the middle. I will definitely miss some if I don't do it this way. And moreover, yeah, okay. And root 100 is directly in the middle. Yeah, we're catching on. Okay. So while I define some things to actually state what the theorem is saying, the motivation here is I would keep this question in mind, which is basically, how much can we generalize this? Now, in what direction and all that, maybe think about that silently. How much can we generalize this? Okay, so in order to make this meaningful, and just to make some of like the inequalities work out nicely, we're only going to consider actually the non-square case. So we're not going to have a root directly in the middle, or a divisor directly in the middle. We're actually going to go even stronger than that. So we'll define, we say that n is square free. If the only square that divides n is 1. D is 1. So, for example, 30 would be square free, but 24 wouldn't be because 4 divides 24. Okay. So basically, we're only going to be considering square free n, and the question is a question which you don't necessarily have to answer, but in so answering it, we will define a couple key terms. So it's useful to answer it. how many square free numbers are there? Meaning how much have we restricted our study by considering only square free numbers? So in order to do that, we'll define the following function. I'm going to move this over there. So let's define. So this is called the Mobius function. And this sends n to -1 to omega of n. I'll say what that is in a second. If n square free, 0 otherwise. So omega of n is the number of distinct prime factors of n. Getting lost in the sauce. Alrighty. So for example, Mobius of 30 would be -1 because it's -1 cubed. Mobius of 20 would be 0 because 20 is not square free. The important thing really, I mean, we actually, to do some of the proofs we're going to talk about, we actually need the Mobius function, but really all we care about is its square. So if that's somehow confusing to you, just think of it as an indicator function for n being square free. Yeah, it spits out 1 if n is square free and 0 if it's not square free. Yeah, what's up?
Can you give an example of where
Mu.
of n is -1?
Yeah, 30. So mu of 30 is -1. So for example, mu of any prime is -1. Mu of any product of two distinct primes is +1, because then there'd be two distinct prime factors. So yeah, I mean, this function has a lot of number theoretic interest in its own right, but it's not super important that you understand exactly how this function works or really any interesting information about it. All we really care about is its square, that it's an indicator function for square free numbers. That's really all we care about. Okay.
Can you explain why we restrict ourselves to square free numbers?
So among other things, the divisors of square free numbers have nice properties in that if you have two divisors of n and one of them is divisible by a prime and the other one isn't, you know they're coprime. So like it's very easy to, to prove coprimality between two divisors of a number if you know that that number is square free. Coprimality meaning not sharing any prime factors between them. Does that answer your question? I mean, there's a lot of other properties, but in particular, this doesn't happen, right? If you're square free, you're definitely not square. Okay, now the whole point here is, my original question was how much have we restricted our study? One way you could answer that is to look at this quantity. So for some large real number x, basically what's the average value of Mobius squared of n? Or another way to ask this, how many square free numbers are there less than a given threshold x? And this is a famous result in analytic number theory. This is 6 over pi squared x plus the low of x. 6 over pi squared x, the 6 over pi squared is coming from zeta function, if you've ever seen zeta of 2. If not, here's pi. 6 over pi squared is like 0.6-ish. Point being, the headline here is that roughly 60% of numbers are square free, so we haven't chopped away that. We're basically considering more than half of numbers, so it's not like we're considering like 1% of numbers or something. That's the headline here. Okay, and big O, little o notation. If we don't know that, just basically consider this to be a negligible error. This is basically saying that roughly 6 over pi squared x of numbers are square free. Okay. Okay, so now that we've defined some things, let's come back to our question. So how much can we generalize the notion that half of the divisors of a number sit below the square root and half sit above? So let's rewrite this in like proper math notation. So what's up?
So that is the default notation or the small o notation? Because
That is small o, small o,
oh, okay.
little o. Yeah, if I put a bar above it, that means a little o.
Okay.
And if I don't, it's big. I actually don't think I'll use a big O. Yeah, I'll specify if I do, because now I will remember. Okay. Yeah, to your earlier point, Evelyn, the fact that we restrict the square free numbers might not even be, like why we do that might not even be apparent by the end of the talk, but if you look into the details of like what's happening, you'll see that that's a useful thing to do. Okay. Okay. So this is just rewriting how this phenomenon. So this is saying that the number of divisors of n is twice the number of divisors of n which lie below the square root. Yeah. So this allows us to generalize properly. Now, how are we going to do that? Well, for one, well, one thing we could do is, if I rewrite it like this, there seems to be some resonance happening here. Maybe the 2 here, if we replaced it with a k, maybe that would cause a k to happen here or something like that. That's like a rough guess. But another way to say that is less than the how do I say this? Below the 1/2 power of n lies half of all divisors. Maybe below the 1/k power of n lies 1/k of all the divisors of n, something like that. So let's say replace 2 with k. Okay, and so maybe our first guess at a generalization would be something like this. And maybe we don't get equality, say. Maybe, let's say we get an inequality. So at least 1/k of the divisors. So at least 1/k of the divisors, if you divide this k over. At least 1/k of the total divisors lie less than n to the 1/k. You don't answer, you don't answer. What do we think? Do you think that this is factual or not? 5, 4, 3. No, it doesn't work. This doesn't work. This is wrong. Why is this wrong? There's a heuristic argument that you can make, which probably wouldn't make sense until I explain the full generality in which we do generalize this. And I won't talk about the argument either. However, there's an inequality that will be sharp in some of the theorems that we'll state, and I'll reference back to why this doesn't work in that context. Okay, so our second guess is as follows. But one way to interpret why this is wrong is that somehow the 1 here is too big. So what you need to do is make it small. Now, you can't just change it with another constant. What you need is some function that's like decreasing with the size of the divisor in some way. So that brings us to our second way in which we're going to generalize this. I'll replace replace 1 with h of d. Okay. Now, so h is going to be some function depending on our divisor. So our second guess is going to be something like this. And now I'm going to add a little of 1. Maybe we incur some error. Now, the weird thing here is that usually when you have little of 1, you're thinking, this is asymptotic notation, you're thinking something's going to 0 as n goes to infinity, something like that. However, if you think about it, the complexity of what's happening here doesn't really increase if the divisors don't increase. So you could let n be a prime and let that go to infinity, but the number of terms of our sum is not really going to increase. So really what we should say, if you think about it, and this is how all the theorems are stated. Little of 1 goes to 0. So instead of as n goes to infinity, or as like k goes to infinity, little of 1 is tending to 0 as the number of prime factors tends to infinity. And that makes sense because this sum, you're going to have more divisors if you have more prime divisors. And so more things are happening in this sum for error to lessen over time. That's kind of the idea. Okay, and this is not too far off. So this is what Alladi got in the 80s. But we need, I mean, it'd be nice if we just had this for any function h, but of course we need to restrict our focus on h a little bit. So for that we make another definition. So h is a multiplicative function. So a multiplicative function is a function h such that if you put two inputs like this, it'll split up over those inputs. So it's kind of like a homomorphism from algebra, something like that. Notice that the function h of n equals 1 is a multiplicative function. It's actually what's called a completely multiplicative function, meaning that you actually don't need this condition where m and n are restricted to be coprime. There's other examples of multiplicative functions. We don't really need to consider them, but I mean the main idea with them is that if h is multiplicative, then you really only need to know what's happening at the prime power values of h. So basically by the fundamental theorem of arithmetic, right, you can just factor n as prime powers, and then you can use multiplicativity. All prime powers are going to be coprime to each other, and you can split it up as like h of n equals. Like that. Something like that. Now, we only care about square-free numbers for reasons I haven't made super obvious. And so we actually only need to know on h of p for prime values, because obviously if n is square-free, it's not going to have any prime powers dividing it that are greater than 1. Okay. So I think now we're ready to state the first theorem. And henceforth, so this is the theorem of Alladi. He did this with Erdős and a guy from UT Austin, Jeffrey Vaaler, who I will now refer to the trio of them as AEV. So for all k, I think you can have k be 2, all square-free n. All multiplicative functions satisfying this inequality, which I'll get back to in a second. You basically have our second guess, except k is replaced with 2k. And again, we're going to have little of 1 tending to 0 as the number of prime factors tends to infinity.
And it's equality, it's not an inequality?
It is an inequality. Thank you for catching that. Let me make sure I have that right now that you pointed that out.
I thought it was 4.
It's 4. It's 4 in my theorem. This is a theorem. Yeah. Okay. Yep, checks out. Now, like I said, this was improved basically to exactly what we had here by Sanarajan at Stanford, although that's kind of a misnomer to say, because like I said, he was 17 at the time and was not employed at Stanford at the time. But basically, he showed that we can replace 2k with k. So, I mean, there's a couple ways to interpret like how this is actually relating to our like original question. But you can kind of think of these functions as weights. I mean, this inequality in its own right is useful in analytic number theory. I mean, these sort of divisor sum things happen all the time. It's always nice to restrict to a smaller range of summation if you can. But yeah, I mean, this shouldn't be the full truth, actually. So AEV conjectured the following. That k can be replaced by 4. Which kind of makes sense because, so note the following. If n is square free, and h of p c. So h is constant on primes, which remember, we only really need information on primes to talk about h for all n. Then h of n. So you basically have this expression for h of n if h is constant. Now, why did I bring that up now? One thing I did want to note is that this inequality is sharp, and the heuristic I was talking about earlier as to why that's wrong is basically because this inequality is sharp. So by that I mean, yeah, if you let k be 2, you get an upper bound of 1 here. And k being 2 is exactly our original inequality here. So letting k be bigger, you have to force h of p to be smaller. Yeah. Oh, so the reason I brought this up now is because if basically c is going to be small because c has to be sandwiched between 0 and 1 over k minus 1 if you let k be, say, I mean, if k is at least 2, or at least 3, sorry, then this is already 1/2. And so this, you know, as the prime factors are growing, the divisors with more prime factors are usually larger, and so they should take up less space in the sum proportionately. So actually, having this only be a constant multiple of this side kind of makes sense if you think about it a little bit. Okay. Now, this is what Alladi kind of tasked me with, and I was like, you know, hell no. But what I could show is the following. So I'll write what we want, and then I'll show what I actually did. That's what we want. Now, I've left these spaces here very meticulously because, in fact, we don't have this. So I'll just say under same conditions for the sake of brevity. So basically, same bounds on H, same range for K. The only difference now is we're going to average over all n. Okay. Now, however, obviously we're not considering all n, right? We said we were only thinking about square free n. And so the way we solve that is we just stick Mobius squared n in here. So that these sums are only being counted when n is square free. Yeah? Okay. So that's the main theorem.
And that's proven.
That's proven. That is. Or I should say, I have a write-up for it, and let this talk be an open invitation to anyone who wants to look over that paper and ensure its correctness. Is probably a better way to say it. Theorem question mark? Theorem to be continued. Okay. Now, okay, I'll give a sketch of the proof. So, yeah. Now, like many theorems, this theorem is multiple theorems in the trench coat. And that sort of gives insight on how to actually attack proving this. Often in math, you'll find that just because you get a better result doesn't mean that the method you used is any more usable, you know? So while Sound got a better result, AEV's paper is actually a lot more informative on how to move forward and improve. So these two sub-theorems I'm about to state are basically exactly what AEV proved, but just in the average out setting. Okay. So before I'll state them, I'll just say the way it works is we prove the simple case, so to speak. And then we show that this implies everything. Okay, so any idea on what the simple case might be? 5, 4, 3. Okay. It's the case where h is constant on primes. So, yeah. I'll just say star. So, star is true for h so it's constant on primes, and that constant obeys the size bounds that we wanted before. Okay. And then theorem B is a bit trickier to state. So how do we show that this is like the sufficient case? Well, we have to define the following quantity. So basically what we do is the quantity, as I'm writing it down, is going to look quite scary. But to keep in mind, it's basically, I might be saying this backwards, but it's basically the right-hand side of star divided by the left-hand side, or perhaps vice versa. So this quantity okay. So this quantity decreases as h increases. Okay. Now, why does this imply everything? Well, essentially what this is saying is that this inequality is worse or like harder to show whenever h is bigger. Okay, well, we have it for a constant case, and we know that that constant exists in a closed interval. So if you have some other function which is not constant, it's sufficient to take that function, which exists at various different prime values, and increase each of those prime values to the largest value that it takes on primes. And then it's suddenly constant on primes, but you've handled that case. So that's kind of the idea. Now, the proof of these is not, proof of A is not very interesting. I like these TikTok recipes where they kind of give you like high protein desserts. But one thing about these TikToks is that they don't really give you amounts or the order in which to add them, which isn't always important depending on the recipe. But the point is, I'm going to kind of give you like the TikTok recipe version of the proof of A as opposed to like a sketch. And I'll give you a sketch of B. Okay. So, should I write that? I'm going to write that. So what goes into this? Well, I mean, just a typical thing you would do in an analytic number theory course is the Abel summation formula, which I won't write down here. But basically, if you have a sum involving, if you have a sum like this, where f is like, call it like a calculus function. So it's some nice smooth function, you could say like in, C2 or something. It has enough derivatives that you can play with it and talk about it in an analytic context. And A sub n is some number theoretic sequence, maybe some sequence of divisors or something. You can handle this sort of summation given the Abel summation formula. Okay, and the other thing is just a bunch of propositions that you apply in the correct order. One of which I'll state here, just because, I mean, this is an analytic number theory talk. It'd be nice if the zeta function reared its head for if only a moment. It won't actually rear its head. However, an Euler product will rear its head, if you know what that is, and that is very much related to zeta functions. So I think that will suffice. Okay. And it'll just give you a flavor of like the kind of things that go into it. Okay. So, proposition. Should not have this on the same line. Yeah, okay. So I mean, you can prove this for all complex z, but of course, I mean, there's nothing complex happening. You don't need it for complex. We have the following. Okay, gamma is the gamma function. F0 is this Euler product thing that I promised you, which is this. So it's the product over primes of this thing. Which, if you've ever done analytic number theory, all you essentially do is you try to write this as a generating function, and then you try to extract the pole at s equals 1. And the pole essentially looks like this, except it's a pole of order z, And that basically contributes this log and this gamma, roughly speaking. Okay. That's the TikTok recipe version of the proof of A. Okay. So I'll give a more detailed sketch of B because that excites me more. Okay. Any questions thus far? Too many questions? Right on.
What's inside the bracket? What is like
Here, 1 plus a little of 1. Yeah, I'm writing kind of fast. So in other words, this is asymptotically equal to this. Yeah. Some people don't have the 1 plus a little of 1. They just write like that. It's another symbol. Okay. So sketch of proof of 3b. And I'm going to need more space than what I have erased. So, I mean, the idea is, okay, let's go back to what theorem B even fucking says, right? So theorem B is saying that this thing should be decreasing as h increases. Okay. Now, remember, h is a multiplicative function. It suffices, and we're only summing over square free n. It suffices to understand what's happening to h at one particular prime value. So if you increase h at one prime value, and this thing decreases, that's good enough. So that's basically what we'll show. Because then you could just do it to each prime successively, and then the whole thing would increase. Okay. So suffices to increase h at p and see what happens. Okay. Well, in order to do that, we're going to have to rewrite this, which there's lots of long calculations with this thing, and I will not do them here. But the idea is you can split the top sum and the bottom sum, the n summations, in terms of those n for which p divides and which p does not divide. Again, we're fixing a prime p. Okay. And the benefit of that is that this thing is going to have some h's in it, and so is this thing. But h is multiplicative, and the rest of n is not going to divide p, or p is not going to divide the rest of n, because n is square free, and p only divides p. Meaning, basically you can factor h of p out of this, and you'll get some other term, which I'm going to call a and c respectively, and it's going to look like this. So clearly I'm suppressing a lot, but that's for both of our mental healths. But the important bit is that A, B, C, and D don't depend on the value of h at p. So you can almost think of this expression for r now as a function in h of p. And you can kind of like do d by dh of p of this, just like apply a first derivative to this. And if you do that, you'll basically see that rxh, or rxk, h will decrease as h of p increases. If and only if AD minus BC is less than 0. Basically, you take the derivative of this, you're going to get a square in the denominator, and the numerator is going to be AD minus BC. If that's less than 0, the derivative is negative, this thing is decreasing. Okay. Now, this is a tall order, given that we don't even know what A, B, C, and D are. But luckily, I do. And after a lot of work, you can factor this expression that I haven't written. And you require the following calculus lemma. Okay. So f is just some function from the positive reals to the power of positive reals, which is increasing, differentiable, function satisfying a size bound, which is this. So x to the little of 1, here little of 1 is tending to 0 as x tends to infinity. The point is that x is growing smaller than polynomial. So it's not, it's not a x to the 1 over 100 or something. It's something growing much slower than that. So think log, think powers of log, something like that. And then we're also going to define gamma to be this sort of like convolution thing. So, yeah. And then what this theorem says, and this is not hard to show, this is just like you literally take derivatives, but then gamma of n has a critical point at x equals root n and is decreasing on root n to n. So I'll draw a picture of what this means. So if we take the graph of f, which again is some slow increasing function, so it's going to look something like this. Yeah. Think log. And then gamma is going to look something like this. Oh, I didn't even say what n is. Just think n is some large positive real number. Think a million. I won't quantify it in the statement because it's too late. Okay. And what this is saying is that the graph of omega n should look something like this, where this is root n, and this is n. So basically, we have a peak here, but it's decreasing here. Okay, so why is this useful in the slightest? I'm going to leave the theorem here, and then I'm going to kind of... How do these professors manage this corner so gracefully? Okay. The whole point is that we can factorize this expression AD minus BC as something that looks like something using this. So after a bunch of calculations, what you get is that AD minus BC is just some positive stuff times this thing. Okay. Where, remember, P is the prime that we fixed. I can actually tell you what n is here. So basically the only thing I'll define in this entire proof. N is x to the 1 plus 1 over k over p. And, well, I don't need to define gamma. Gamma is defined in terms of f. What is f? F is something depending on h, and that's all I'll say. The point is, f all you need to know is that f does satisfy this size bound, and it is increasing, and it is differentiable. That's all we need to know. But the point is that x and x over p are both in the interval root n to n based on this, if you think about how these two relate in size to this thing. And x over p is always going to be less than x. This function is decreasing, so this thing is always going to be bigger than this thing. This minus this is negative. This is positive times a negative. AD minus BC is less than 0. And that's basically the entirety of the proof minus about a billion details. Okay. So this is how you prove the main result of my paper. And the question is, how does one move forward from this? So, I mean, we have this averaged result, which I guess I erased what the conjecture was. But the conjecture is basically that this works without the summation in n. So you don't need to average for this to be true. Okay, well, how do we prove that? Well, I don't know how to prove that. I would be talking about that instead if I did. However, yeah, hopefully not on the thing I just erased. What's up?
No, about that, you say that since that quantity decreases as h increases, you're saying if we increase h, it becomes harder to prove.
It becomes, the constant here becomes worse, basically. So this constant would be smaller.
So if
Yeah.
for all the h's for all the things defined, why is it not enough to just prove it to the highest possible h for a given k? So why is it not enough to just set h of p to 1 over k minus 1?
That's a good point. There is a reason. I've forgotten what the reason is. I will have to look over the paper again and get you an answer to that. But there is a reason. I'll give myself 30 more seconds, or maybe like 15 or 17 to figure out why. But there is a reason. I mean, it's also worth saying that like you can evaluate these sums directly if you just fix h to be constant on primes. So it's worth evaluating. I mean, I guess the only thing that changes is basically like how you smush these together to get the main theorem.
Because you adapted those terms from the original tutor.
Yeah, and
they
they said that, and they probably had a good reason for saying that. And I think I knew the reason that they said that at one point, but that point and this point have evidently diverged. But yeah. Okay. But as far as moving forward, how much time I got? Okay, that's enough time. So again, going back to the fact that AEV's paper is a lot less opaque as to like how to adapt their argument to move forward. At one point in their proof, they consider the following. So they basically say this. Okay, so write some large natural number n as a product of k distinct natural numbers. Or not necessarily distinct, just their natural numbers. Then at least one of di satisfy so at least one of these have to be less than n to the 1 over k, which if you think about it, I mean, a very simple argument is, suppose that they're all greater than n to the 1 over k, then their product must be greater than n, but they equal n. this should be a big N. Now, how do they use this fact? Read the paper. But heuristically, we should expect k over 2 of them. Meaning, if you think about it like the most balanced representation d1 up to dk would be like if they were all actually equal to n to the 1 over k, which would happen if n was a kth power. Of course, we're only thinking about square free n, but bear with me. And so, like based on that, the second you start messing with that balanced representation, you should have some go above and some go below, and they should maybe do that symmetrically. That's like kind of the idea. So basically they think that they should be off by a factor of k over 2, is kind of what they said. They got 2k, k over 2, 2k over k over 2 gives you 4. So that's basically the entire reason that they think the answer, the constant in front there should be 4 without the summation. So like the whole idea might be how do you quantify this heuristic? So one way you could do that is the following. So first, we're going to define this is known as like the k-fold divisor function, tau k of n. So this is just counting the number of ways to write n as a product of k natural numbers with multiplicity. So like you can permute them, and that would count as a unique representation, which won't affect how we're thinking about it here, but for the sake of completeness. And then g sub k we're going to define in the following way. It's going to be a sum over the same variables. However, we're summing this instead. So we're counting in each such representation how many of the di are actually less than n to the 1 over k. So think of this as averaging over all the such representations. How many of them will be less than n to the 1 over k? So one thing you could maybe conjecture based on this heuristic is that this should be on average k over 2, roughly. Again, little of 1 is tending to 0 as omega n tends to infinity. So this might be one way. If you were to show this, I mean, I haven't showed that this directly implies the full conjecture, but it is at least like morally equivalent to what they were saying. It also might be worthwhile to like go through their paper and find a similar formulation, which I imagine wouldn't be as like robust as this, but you would probably come up with something similar that might actually directly imply the full conjecture. I've tried about like a bunch of different methods to try to prove this, to no avail. But it's very like combinatorial in nature, as was AEV's original proof. But yeah, so maybe if you're looking for like a area of exploration, maybe try here. Yeah, that's all I got for y'all. Yeah, thank you. Any other questions that I may or may not be able to answer? What's up, Curtis?
Yeah, so I might just not be in the loop here.
Mm-hmm. You did come late.
I'm sorry. Legitimately after sleep.
It's okay. You're allowed to fall asleep.
When I woke up, I realized it was
Yeah, what's your question?
yeah, so he described
Yes.
Those expressions a weight function?
No. So I mean, the way to think about it is, you could do 1 over x times 1 over x on both sides, and then they would both be an average of what they're summing over, is the idea. So what you missed was the full conjecture is that this holds true without the sum and the Mobius squared. And yeah, usually in number theory, the 1 over x is just considered like a normalizing factor, and you don't really consider dividing by it, especially because a lot of the expressions, like a very common first foray into number theory is like computing summatory functions, like basically computing this. Computing like the sum function of a number theoretic function, because these functions are usually pretty randomly behaved, so you don't really, I mean, you care about maybe what's, some of the particular values are doing, but you really care about, well, one statistic you could first glean from them is what they're doing on the average. And basically anything that you do to understand that is going to be based on this, not based on this. Yeah. Does that answer your question?
Yeah, so maybe you could maybe get rid of the Mobius there and say that it's 1 over x instead, or?
No, I mean, we need to be summing in order for this to be like a valid statement in the context of the theorem. Yeah, without the sum in x would just be an arbitrary variable, right?
Right, but what's...
Or if you like, I think this isn't quite averagey enough for what you consider to be an average. I think that's probably a better way to explain your gripe. Yeah. Any other questions? Yeah, that's it.
Does this have any applications to any other area of math, or?
Yeah, so when Alladi first posed this problem to me, he told me to read this paper he wrote with Erdős as well that was in probabilistic number theory, which, okay, so this isn't like an application of this theorem, but just to give you like a flavor of the kind of thing that it was used to so the idea is that this was used to show something in probabilistic number theory. That's why he considered it in the first place. So this is like a standard kind of theorem in, what do you call it? In probabilistic number theory. So this is, it's called the Erdős-Katz theorem. And it says that, among other things, this is one special case, but basically the function omega n is what's called, or not completely, but an additive function, which is defined very similar to multiplicative functions, but just with addition. And so it applies to more general additive functions, but basically what it says is that omega n behaves like a normal distribution, something like this. With mean, log n, and variance root log n. So it's well known that the mean in this sense of omega n, if you sum omega n divided by x, you'll get roughly log x in that case. But this is a much deeper theorem, which basically says that how it strays from that mean has variance root log n. So it was used to prove something kind of like that. Yeah. Any other questions, folks?
So you were saying that one of the main reasons you wanted to write this paper is because you were inviting
Yeah.
So would you like to?
Yeah, you let me talk. Okay. So yeah, I mean, basically the paper is written. Now that I'm in the tech class, the latex class, here. I realize that I should probably make it look a little nicer than it does right now. But beyond that, it's written and, in my estimation, correct, but perhaps not in your estimation. If you'd like to look it over in more detail, I'd be happy to talk your ear off about every last detail that I omitted here. Yeah, so feel free to talk to me about that at any point, including now. No, okay. Anything else?